Hey, this is David Lewis talking from the University of Wisconsin, Eau Claire, and he's going to talk to us, as you can now see on the screen, but unfortunately not in slideshow, 2 centuries of aromatic hydrocarbons because there's been absolutely no celebration of the bicentenary benzene. There were massive celebrations in 1925, and as David pointed out to me a couple of weeks ago, absolutely nothing this year. So, David, you're going to make up for the terrible omission. Please get started.
Thanks, Peter, and thanks for letting me talk to the group. It's early in the morning here, and as Peter knows, I have an axiom now that I'm retired that 8 o'clock should only come once a day. Um, so right now it's 8 o'clock. It's actually 8:10, so we're late. So yes, benzene, and um, I didn't realize I had quite as close a connection with benzene as I do because it turns out that on June the 16th, 1825, Michael Faraday's paper was read before the Royal Society. On June the 16th, 1922, Edwin Lewis was born in Thornaby-on-Tees, England. And that's my dad. So Benzene shares a birthday with my father. Just a little weirdness there. So the man of the hour here is Michael Faraday. And scientist extraordinaire is the minimum you can say about this man. He was born in Surrey, but he was not born into wealth. And so he had only a basic school education and was largely self-educated. This is thanks to the 7-year apprenticeship that he had with George Rebaugh. Rebaugh allowed him to read the books in the bookstore and the bindery. And so Faraday was absolutely fascinated with science, and he read everything he could get his hands on. In 1805, this was 3 years after Alessandro Volta came up with his pile, and so electricity was a really hot topic. Now, Humphrey Davy, of course, was using an incredibly large voltaic pile to generate the electricity needed to make sodium and potassium, amongst other elements. And Rebaugh arranged for William Dance to buy tickets for Faraday to go attend Humphrey Davy's lectures. Faraday's apprenticeship ended in 1812, and being at a bookbinder, he then bound up his notes that he'd taken from Davy's lectures and presented Davy with a 300-page book. Davy actually was rather impressed, and so it was fortunate that an apprenticeship or an assistantship came open, and Faraday became Davy's assistant. This was also due to a fortuitous accident with nitrogen trichloride. In 11 years, Faraday had been elected an FRS, and he was elected a foreign member of scientific academies in America, Sweden, and France. And in 1833, he became the first Fullerian professor at the Royal Institution. Faraday's religious beliefs prevented him or dissuaded him from accepting a knighthood or burial at Westminster Abbey. The guy was absolutely brilliant. Yeah. Think about what he accomplished, and yet he never learned calculus. Now, we can take a quick look at his scientific contributions. To chemistry, he gave us electrochemistry, and physics, he gave electromagnetism. So electricity was the one common thread. His discovery of benzene, he came up with an early design for a gas burner that presaged the Bunsen burner, and he popularized the terms cathode, anode, electrode, and ion. In physics, the physicists love him because we've got electromagnetism, not electromagnetism, magnetoelectric induction, and magnetic fields and lines of force. The fact that he had no calculus meant that James Clerk Maxwell then took what Faraday had done, and from it developed his theory of electromagnetism. So we're going to talk about benzene, and we're going to talk a lot about benzene. So let's take a look at the timeline. As I say, on my father's birthday in 1825, we had the first isolation of benzene from illuminating oil. The first big question is, does benzene obey the usual rules of chemistry? 1828, Wöhler's urea synthesis basically said, yes, organic compounds also obey the regular rules of chemistry. In 1833, the molecular formula for benzene was established. And then the next big advance was 1858 to 1861. And the question to be answered there is, how can you talk about a structure without a basis? And the structural theory of organic chemistry was developed in those 3 years. 1865, Kekulé came up with his structure for benzene. And in the ensuing 2 decades, there were a number of refinements of the structure of benzene itself. In 1916, G.N. Lewis came up with his octet rule. And, actually, look at that. I can do something here, can't I? I can correct the spelling errors. 1931, the question that has fascinated chemists for the 200 years that we've had benzene is, why is it so unreactive? And the first really solid theoretical explanation came from Erich Kekulé, with his molecular orbital model for benzene and the concept of aromaticity and anti-aromaticity. 2 years later, Linus Pauling and his student Wieland came up with resonance theory. In 1936, measurements started on the aromatic resonance stabilization energy of the benzene ring. And then in 1941, Erich Claus came up with the Claus sextets. From 1961 to 62, we now move outside of benzene. Still monocyclic compounds, but now, can you have bigger aromatic systems than benzene itself? And so we're looking at the limits of aromaticity. And then from the 1990s until the present day, benzene has become a favorite target of theoreticians. So let's begin with Michael Faraday. And here is the paper in the, it would have helped if I'd put the journal. Of course, this is the Philosophical Transactions of the Royal Society, 1825, on new compounds of carbon and hydrogen and on certain other products obtained during the decomposition of oil by heat. This is Faraday's bicarburet of hydrogen. The bicarburet, because carbon had an equivalent weight of 6 and hydrogen had an equivalent weight of 1. In modern terms, the empirical formula would be CH, but given that the equivalent weight was used by Faraday and others of his contemporaries, we had CH became C2H because you needed double atoms of carbon. His work was reappraised in 1968 by Kaiser, who took a look at Faraday's starting materials and then used analytical methods from the middle of the 20th century. And what he found was that Faraday had actually isolated benzene from a mixture that had at least 300 compounds present in quantities of 0.1% or higher. So it's quite an experimental feat to actually do this. So the first advance, Friedrich Wöhler, who had wanted to be an obstetrician, but gave up babies for chemistry, and we are grateful for that. Wöhler was the first. He came up with the synthesis of urea quite by accident. The thing about Wöhler's urea synthesis is it's given rise to a really enduring myth. It's a very refractory myth that his synthesis ended vitalism. It didn't, because it wasn't until 1848 when Hermann Kolbe published the unambiguous synthesis of an undeniably organic acetic acid from its elements that that vitalism finally began to die. Sorry, senior moment there. So we need to establish a molecular formula. Here we have a page from Mitscherlich's Annalen der Physik. And we find here that this is a very careful experimental work. He first looked at the specific gravity of the vapor, the density of the vapor. And from that, he came up with a molecular weight of 77, which is very close to the 78 that we have from the modern formula. The other thing that he did was he confirmed the empirical formula that Faraday had found of CH. And his data give us CH 0.98, which is pretty good. So Mitscherlich came up with the molecular formula. Between 1858 and 1861, the structural theory of organic chemistry arose. There are three main players in this particular development. Kekulé was the first to publish, and he published in the Annalen. Archibald Scott Cooper was a student in Adolf Wurz's lab at the time, and because Wurz was not a member of the Académie des Sciences, he could not read Cooper's paper to the Académie directly. He had to find a sponsor. And the delay caused by that meant that Cooper's paper appeared 6 weeks after Kekulé's. Kekulé basically then built on that. Cooper ended up very frail. He went through a couple of nervous breakdowns, which we would call them today. But it's Cooper's version of the theory that was closer to the modern version. But neither Cooper nor Kekulé saw the real power in the theories that they had come up with. For my friend Jeff Seaman, who would absolutely have a heart attack if I didn't have at least one dead Russian in my talk, the really useful form of structural theory was developed by Alexander Mikhailovich Butlerov at Kazan University. Butlerov is a great Russian organic chemist, and he gave a talk at the Speyer conference in 1861, and Emil Erlenmeyer was there and pressed him to publish it in his Zeitschrift für Chemie in 1861. So let's take a look at Kekulé's structures. The 5 black and white ones up the top are from Kekulé's original paper. It's in French because at the time he was in Belgium. He was at Gand. And so he came up with first, structure 1 is an open chain. These are what Kolbe called Kekulé confusion sausage formulas. And it's actually a pretty good name. The first structure there is an open chain, chaîne ouverte. And you've got the 6 carbons there, but there's no closure of the ring. This was the first time that a cyclic structure for benzene had been proposed. And the idea that organic compounds could exist as cyclic compounds was fairly unusual. And so structure 2 here, we have the open chain, chaîne ouverte, chaîne fermée rather. And you can see the 2 arrows indicate that these carbons are bonded. So here we have benzene, and then here we have chlorobenzene, and here we have dichlorobenzene. And underneath here, notice that here the two chlorines are attached to atoms at the ends of the long sausage bond. Here they are on, they're close to each other. All right. Now, Kekulé's formula had some troubles. First off, obviously, it predicted two orthodichlorobenzenes. And so the race was on to find the best structure for benzene. Now, at the time, the concept of ring strain, which for which we thank Adolf von Baeyer, the concept of ring strain was not actually a concept. And so the idea that a three-membered ring would be unusually reactive was not a particularly, was not actually known at the time. And so what we've got here are Dewar's paper on not benzene, but actually on a set of models. He came up with a set of models that here, the models are rigidly held in a square or a cross. Here, there's flexibility at the center, and these can then link up. And when you take a look, you see that there's interesting ones. This structure here is, in fact, Kekulé's formula for benzene. This structure here is down here, and this is the one that we have in textbooks these days that is purported to be duobenzene. He got his name on it, but he actually never suggested which of these structures could actually correspond to benzene. So you've got here, this is an interesting molecule. It'd be fun to make that. Here we have a cumulene, a methylcumulene. This one is an interesting one. I think might be a little ring strain in there. And then this one is a bismethylene bicyclobutane, probably an excellent explosive. But in any case, what Dewar was pointing out was that using his models, you could come up with a number of structures for benzene. He never actually proposed which of these structures should be used. Then we have Adolf Karl Ludwig Claus, who had a paper that he published in the Berichte über die Behandlungen der Naturforschenden Gesellschaft zu Freiburg im Breisgau. Whoa, I love it. In any case, Claus basically said, look, you cannot have multiple bonds because multiple bonds mean you get two orthoisomers, and only one, and so there's only one orthoisomer known. What he proposed were long bonds that transversed the ring, and this would then give you a system that is all saturated. Albert Ladenburg was a particularly strong proponent of the idea that there were no double bonds in benzene. So he got rid of the double bonds, and instead he replaced them with transannular bonds in this arrangement. Now this is prismane, the triangular prismane. If you take a look down on the top, there is another thing you can do to this molecule, which is to twist the upper carbon through 60 degrees. And if you do that, you wind up with a trigonal antiprism. Ladenburg's objections were really based on the fact that benzene did not react like an unsaturated molecule. It reacted like a saturated hydrocarbon. And so here, all of these, all the carbons here are saturated. But the problem is, of course, that he didn't realize that 3- and 4-membered rings would have unusual reactivity. And then we get Henry Edward Armstrong, the curmudgeon's curmudgeon in a lot of ways. Apparently, Armstrong, amongst other things, wrote a letter to the Times chastising them for having split an infinitive. But in any case, Armstrong basically came up with the idea that of the bonding affinities in the 6 carbons of benzene, 12 there were affinities used to form the carbon-hydrogen bonds. There were affinities to form the carbon-carbon bonds, and the 6 remaining affinities were directed generally towards the center of a ring, towards the center of the ring. And so these were not localized in the way that the other bonds were. He got very close to a modern picture. Here we have Baeyer. In 1888, Baeyer suggested this star-like structure where now you've got carbons in the middle here and you've got hydrogens on the periphery. His hydrogens now are bonded to 2, but what I find interesting here is that Baeyer suggested that these affinities directed into the center of the ring were actually not in the plane of the ring, but orthogonal to it. At least he suggested that was a possibility and well worth looking at. And then we have Johannes Thiele. And Johannes Thiele was working with conjugated systems, and he basically came up with his concept of partial valences between adjacent carbons that are formally linked by a single bond. And so he was able to then come up with this partial valence formula for benzene. Now, let's go back. Kekulé's model had problems. He started out with structures that looked like this. Now, here you've got the 6 carbons of benzene, and he's got double bonds. Now, the thing is that if you have this triangular molecule, you can have the double bonds as AB, CD, EF, or you can have the double bonds as BC, DE, AF. And putting substituents on adjacent carbons in this ring means that with this localized model, you wind up with 4 different forms of dibromobenzene. Later, he came up with the idea that perhaps it was instead a regular hexagon and with all 6 positions equivalent. The problem, of course, then was how do you get the equivalence? Well, in 1872, Kekulé basically said, look, obviously, neither of these structures is actually correct, but they both have to be correct. How do we do this? And he suggested that there was, in fact, an extremely rapid equilibrium. Now, in 1803, Berthollet had proposed his concept of equilibrium, and so Kekulé basically said, well, okay, this is a Berthollet equilibrium. It's extremely rapid, and so no double bond exists in one location long enough to react as a double bond. That's a useful explanation. We know it's wrong, but it's a useful explanation. In order for this explanation to hold any water at all, though, one had to actually show that benzene was a planar hexagonal molecule. And this was done by Wilhelm Kerner, who moved to Italy for his health, amongst other things, and has gone down in history as Guglielmo Kerner. And you can see here This is his paper. It is in Italian. Kerner was a very accomplished experimentalist. When you take a look at what he had to do, he had to separate all these compounds, and he did so mainly by distillation. You think about what that took. Think of the 3-dibromobenzenes and doing a distillation back in 1874 here. It's quite something. So now let's move to the 20th century. We better move quickly too. I'm running over. This is Erich Hückel, who came up with the first serious theoretical explanation of benzene's reactivity and lack thereof. Here we have his pictures of the pi molecular orbitals of benzene. And from this, we came up with Hückel aromaticity, and there were 4 criteria that are needed. First, the system must be planar, it must be conjugated, it must be fully delocalized, and it must contain 4n plus 2 pi electrons, or an odd number of electron pairs. If it has an even number of electron pairs, the Hückel theory predicts that this molecule will be anti-aromatic and a diradical. So now let's keep moving forward in the 1930s. Here we get to Kistiakovsky's work. And this is looking at the aromatic resonance stabilization energy. Now remember, in 1933, Pauling had proposed resonance theory. And so now, 3 years later, Kistiakovsky is looking at how much does resonance stabilize the benzene molecule. And he came up with a value of about 36 kilocalories per mole. And this has remained remarkably stable over the years. Now, from the 1930s, we move on to the 1960s and 1970s. And here we have Franz Sondheimer, whom we lost at a tragically young age of 54 years old. But Sondheimer came up with the first viable synthesis of 18-annuline, which was the first of the annulenes that demonstrated clearly aromatic behavior. It is interesting that when you add another 12 carbons, and so you get 30 annuline. 30 annuline you would expect should also be aromatic, but it's not. It is in fact the most reactive of the annulenes, and here in the bottom corner is speculation. Admittedly, it is speculation by me, but this molecule is ideally set up to undergo electrocyclizations and sigmatropic rearrangements of hydrogen to ultimately give this 18-annuline derivative. But 30-annuline gave basically a black tar. Now, with the advent of NMR spectroscopy, we could start to take a look at resonance or aromatic systems and anti-aromatic systems. And what we've got up the top here, notice there are an odd number of double bonds in the cumulene. This has 3, this has 5. That means that the 2 ends of the cumulene are coplanar. And so this system has the potential, at least, to be aromatic or anti-aromatic. The blue ones, these molecules, where M is equal to 1, 2, 3, 4, and 5, this is a aromatic system, or presumably aromatic system. Here, with M is equal to 2, 3, 4, with the pentacumulene system, these are anti-aromatic. And if you take a look at the chemical shifts of the exterior and interior protons, the in 14 annuline, or the C14 version of annuline, we see clearly very strongly paramagnetic downfield shifted external protons and strongly upfield shifted internal protons, with exactly the reverse pattern in the anti-aromatic system. This is a pretty paper to read. Now, when you teach organic chemistry to undergrads, you tend to get lazy, and it's very tempting to put the circle in the middle of every ring that is presumably aromatic. But Erich Claus, Swiss chemist, wrote a book, Aromatische Kohlenwasserstoffe, which he published in Berlin. Sorry, he wasn't Swiss, he was German. In 1941. And what he said, or what he came up with, was what we now call the Claus sextets. That is, a ring in which you have 3 double bonds all the time is aromatic, and all other bonds are not. And so if we take a look at phenanthrene, we see that up the top here, we have a structure with 2 Claus sextets and an olefinic double bond. Down the bottom, we have 1 Claus sextet. The Claus made the point that the more of these Claus sextets you get, the more important this is going to be in predicting reactivity. And we know that phenanthrene, it's the 9-10 positions that are the most reactive. So now let's move into the 21st century. Well, NMR spectroscopy comes to the rescue very quickly. If we place an aromatic ring in a magnetic field, we get a ring current. Any cyclic conjugated pi system will generate a ring current. Aromatic compounds exhibit a diatropic ring current. And when we look at a diatropic ring current, this generates a field that reinforces the external field out at the peripheral hydrogens and opposes the external field in the interior of the ring. Anti-aromatic compounds exhibit exactly the opposite. And as we saw back here, we can see diatropic, paratropic, diatropic, paratropic. We get that alternating system. 18-annuline is beautiful because we find that in 18-annuline we see at low temperature, this is done at -40, we see that in fact there are 12 protons resonating down around 9 parts per million, and there are 6 protons resonating at -3 parts per million. That's about a 12 part per million gap. It turns out that the NMR spectrum of 18-annuline is temperature dependent, and there's a coalescence temperature around 25 Celsius, which means that the ring is undergoing some kind of inversion. All those interior protons are becoming exterior and vice versa. But at -40, that is frozen out, and we see here a typical AB type quartet, and here a typical, well, this is a multiplet, and that's what they've called it. The idea of the NMR spectrum came, this NMR spectrum rather, I think I stole from von Schleier's paper. Now, that brings us actually to Paul von Rage-Schleier, whom we lost 11 years ago. Schleier was a prolific theoretical chemist, and his computational studies gave us what we now call the nucleus-independent chemical shift. And this is basically the magnetic shielding at either the geometric center of the aromatic ring or at a location typically 1 angstrom above the center of the ring. The more negative the value, the more strongly aromatic the ring is. And so if we take a look, benzene here at minus 15.1 is aromatic, very much so. Cyclopentadienide anion, minus 17.2. The tropylium cation, minus 7.6. Anaromatic rings of naphthalene, 9.9. If we go to the anti-aromatic system, on the other hand, and these are all computational, of course, cyclobutadiene now, very anti-aromatic, plus 27.6. If the system is not aromatic, and in fact is just aliphatic, we notice that the nucleus-independent chemical shift is very close to 0. So a very small number. So we can see that things are continuing to move. There were a number of papers published in 2024 on benzene and what benzene should do and shouldn't do and what have you. So there, in a nutshell, a very fractured nutshell, is the story of benzene. It's 200 years in 35 minutes. I apologize for being so short, but maybe we can have some questions.
So not to worry, David, not to worry. It happened to the best of us. Well, thank you very much for giving such an interesting talk on such an important compound on the 200th anniversary, and more or less. So thank you very much for being the only person to remember it. I'm sorry it was not more widely recognized. We'll come back to that in a moment. But I haven't actually had any questions yet. So if anybody has any questions for David, please put them in chat. Henry Vepper has been making lots of comments, but I don't think I can read out all of them. But if you can access chat, you can read them. David, there's just four things I wanted to say, I think, and then a question. The first thing is, but the Science Museum itself has 2 interesting artifacts in this context. One is the original sample of benzene, which was in Faraday chemical chest. And the interesting thing about that is it's incredibly pure. I tried to look it up before this talk and I wasn't able to, but it's something like 99.998% pure. It's incredibly pure.
Yeah.
They think the only way he could have done this was by fractional crystallization.
I think that is exactly correct. That as an undergraduate student, I was doing a recrystallization from benzene, and as all beginning students do, I wanted to finish the crystallization by sticking it in ice. And I then found that indeed benzene will crystallize at 6 Celsius. And so I had all these beautiful white crystals in my flask. Oops. But yeah, I'm sure that Faraday resorted to crystallization to purify the benzene. It was one of the, it was still a very new technique. But I'll bet it wasn't just fractional crystallization. I bet actually what he did was he froze and then he allowed it to melt.
Yeah.
And got the pure benzene that way, having the impurities come out in the melt and then collecting the crystals.
Probably didn't even need to freeze anything given what room temperatures were in those days. I don't know. It was April, wasn't it? Hopefully a bit warmer by then.
Well,
I think I was going to say,
yeah, but it was England.
I have a lot of models. They're basically wire models of all the different benzene models you mentioned. It's about a dozen of them altogether. They made them in the 1920s when they were first developing what was then the chemistry gallery. Haven't been on display for years. I was also curious by your mention of Paul von Arstlayer because I think Jeff will probably have a bit of a laugh at this. When I was doing chemistry in the 1970s, there was a rumor that to be a really, really famous and important chemist, you had to have a von in your name. Because there was Paul von Arstlayer and there was William von E. Doering. And we
Yeah,
all thought that if only we could get a Von in the middle of our name, not like in Von Hoffman, but Von something, and then your surname, you become really famous. So that's another thing. By the way, you might be interested to know toward the end of your talk, and I hope I'm not going to embarrass him by saying this, so sorry, Roger, if I embarrass you, but Roger Mallion, who you cited in one of your later papers,
yes,
he's actually with us in this audience. He was
I know. I saw that.
Yes, he was one of
I
my chemistry tutors. He was one of my chemistry tutors at college, and he asked me if he could come along to the talk. And I said, of course, anybody can come to these talks. So he's with us
yeah.
today. So everybody's muted, but a wave out to Roger there. And Jeff is here. Jeff Seaman is here as well.
Is
Uh,
Jeff? Jeff, you must be happy then that there was at least one dead Russian. By the way,
yeah,
uh,
but put your answer
eighteen
in chat. Put your answer in chat.
yeah, 1825. By the way, was the centenary
Yeah,
of the Russian Academy of Sciences, which had
yeah.
been founded in 1725 by Peter the Great.
At the end, put it in chat. So I'm just going to unmute Jeff for a moment. Jeff, do you want to say anything?
Probably wants to say a lot.
Yeah, probably. No, I can't. I've asked him to unmute, but he hasn't done it. Oh well. The trouble is, we do this because we get too much follow. He put a probably
Yeah, yeah.
he
No
probably
problem,
put it
Jay.
in chat. Yes, nice lecture. Yes, a happy friend. Yes, there you are. Okay, so my big question to you is this, and it's a question we were talking about before we started. When, with hindsight, maybe we should have worked on the screen, and that is why. What happened to benzene? And, 1925, you have the tremendous celebration of benzene, and now nothing. It's like Mole. I mean, in 1906, there was a major celebration of Mole. In 1956, there was a major celebration of Mole. Even in 1981, the 175th anniversary, ICI did something. 205, if I hadn't organised a lecture by Tony Travis at the last minute, in England at least, there wouldn't have been anything. So what's gone wrong here?
Well, as I told you, and this is strictly speculation on my part, so I'm not going to put any money on it. But what has happened over the course of my career is that there has been less and less and less looking back at where we came from, and more and more and more focus on what's the latest hot topic. And because of that, I think we have lost an appreciation for what we can get from this earlier work. I mean, preparing for this talk, I was reading stuff that I haven't read in years, and you start to get an appreciation. I mean, well, for example, Faraday's sample of benzene, getting that kind of purity, given the experimental techniques available to him, was incredible. But we've lost an appreciation for that. And now, if you're not on the hot topic, then you're not with it or whatever. So it's an interesting problem. I think that what actually happened was that Faraday was early enough that when Kekulé came along, a bona fide organic chemist, that gradually the focus of organic chemists and on benzene shifted from the molecule itself to Kekulé and the questions that he raised. And it's interesting that in 1865, in 1905, you had the Benzol Fest, and then in 1965, you had another Benzol Fest, but I don't recall whether there was a 150th in 2015. That's a good question. you know, that's a real good question. Now I'm going to have to.
Andrew Rappert just said the 100th anniversary of the curly arrow wasn't celebrated either. So
Yeah,
I don't know. I could have dated the curvy arrow quite so precisely, but there we are. It's a great.
well,
Hmm.
the
You
curved
made that.
arrow is
You made
curved
that.
arrow
By the
is an
way, David,
interesting.
we owe you a very great thanks because unfortunately, everybody, our scheduled speaker, John Powers, had a very sad family event that meant that he couldn't be with us today. And David, who had just by some miracle contacted me a few days earlier to say what happened to the centenary of Benzene. And I got back to him and said, David, can you talk in a week's time about the centenary of Benzene? And he said, I'll give it a go. I don't normally get up at 8 in the morning, but I'll give it a go. And David, you've done it. You've done it splendidly. We all owe you very great thanks for what you did. Thank you very much indeed, David. And thank you very much, everybody, for
Well,
coming to this talk at very short notice, unscheduled notice, but a very important event, as David has demonstrated to us. And I do hope you enjoyed it. Next month,
thank you very much.
next month, we have Jeff Rayner Canham, who is currently on a ship somewhere off the coast of South Africa. He'll be back in Canada next month, and he'll be talking to us. Dying for Work. Dying for Work is about women who did dangerous jobs in the chemical industry, and he'll no doubt show that there was some element of prejudice and all that. So Jeff, next week, once again talking about women and chemistry, but this time it's the angle of them having dangerous jobs. So we look forward to that. He always gives a very good lecture. David giving us a very good lecture. I hope you enjoyed it. I hope you come back next month. And please go away and have a good afternoon. Or in David's case, even a good one. So
A nice
bye,
morning
everybody.
nap.
Bye for now. Bye, David.